Hello, and welcome to another session on data mining. In this lecture series, we're going to talk about how we can evaluate how a machine learning model is going to perform on a given problem. Um, and that is called evaluating and comparing models. So we're going to talk about different strategies of how we can compare the accuracy of different machine learning models and how we can evaluate the accuracy of different machine learning models. So in my opinion, this part of the module is the most important part because this is something that you need to be really careful about when you're developing machine learning models. So the goal of this part of the lecture series is to talk about those experiment design strategies that can enable you to build, evaluate, and compare models. Now we've already talked about how an SVM works or how a k-nearest neighbor classifier works, and that is you feed in some training data with some training labels, and then you train the classifier, and then you're given a test set on which you can use those examples in the test set or in the validation set to evaluate or get an idea of how good or bad your machine learning model is going to be for a given problem. We're going to talk about different strategies and different caveats that are important in developing different machine learning models and deploying them. Okay, so the goals of this lecture is how can we design experiments that allow you to compare two different machine learning models. So if you want to say, if you have a bet with your friend and you say that your classifier is better than theirs, then you would probably need to use some of the tricks that we're going to talk about in this part of the lecture or in this lecture series to be able to do that. Similarly, if you have two machine learning models, you can use these strategies to compare which one of them is better than the other. But you can, for a given classifier, let's say a support vector machine, you can also pick its different hyperparameters. So what kernel should I use? What should be the value of C be? Or if I'm using a k nearest neighbor classifier, what should be the value of K? Or how does the value of K or how the value of C affect the generalization performance of a machine learning model? You would need strategies, these experiment design strategies, to be able to answer those questions. So most of the time when we are developing a machine learning model, we are given a training data set. We hold out a part of that training data set so that we can, for which we know the labels. We use the remaining part for training, and we use this validation part that we have set aside to get an idea of how the classifier is expected to perform in the real world. Okay, so that is the basic structure of how these experiment design strategies go. But what we are going to do is to take a slight detour into the philosophical foundations of data science. Remember, I've already talked about why data science is a science. It's because we use the scientific method in the analysis of data. So that's why it's called data science. And we are going to talk about those experiment design strategies in this part of the lecture. And we'll also be talking about those performance metrics such as accuracy, PR curves, ROC curves, F measures, everything that you would need in order to quantify and measure the performance or the accuracy of a machine learning model. We'll also be talking about some strategies that are used for performance analysis. So how does cross-validation work and what is resampling? So we're going to talk about all of that. But before that, we're going to talk about the scientific method itself. And I think the best, I posted a link to a video by my favorite scientist, Richard Feynman. I love his book. One of his books is called Surely You're Joking, Mr. Feynman. It's a recommended read. And if you want to understand science a bit better, I think it's a good way of understanding that by reading this book. Or if you're just interested in understanding the scientific method, I think he gives in that video a very succinct and a very concise explanation of how the scientific method is applicable to different areas in science. So if you talk about any problem in science, you've got a hypothesis or what he calls a guess. Once you have a guess, let's say support vector machines are going to do very well on this particular problem. That's now your guess. Then what you do is you design an experiment and you evaluate the consequences of that guess. That is, does does my hypothesis hold in this case? And then I go ahead and compare the results. So does it perform really well on a large enough independent test set? If it does, yes, well and good. If it doesn't, then it's wrong. That means my guess is wrong because the experiment has shown me, if the experiment has been designed well enough, then that shows me that the original guess I made about the choice of a certain classifier or machine learning model or a certain type set of hyperparameters, then that guess is wrong. We can also use it for so many other things. But the most important thing, and I really recommend that we never forget this, is once we have the results from a machine learning model, it doesn't result from an experiment. It doesn't matter how beautiful your theory is or how beautiful your guess is. If it doesn't agree with experiment, it's wrong. It doesn't matter how smart that particular guess is or whoever made that guess. The real thing is if it doesn't agree with experiment, then you need to update your guess. We that is a strategy that we are going to use when selecting which machine learning model to use for a given problem, what features to use for a given problem, what hyperparameter settings should we use for a given problem. So let's say if our objective is to find what model fits the best for a given problem, we design an experiment in which we have a large enough validation set. And if you recall from the very first lectures of this module, we've been talking about the goal of machine learning is not to memorize a given training data set, but it is to develop machine learning models that generalize to a given test set. That is, they produce correct predictions on a large enough test set so that we can say that it has solved that problem. Okay, so that's the real goal of this, and we're going to use these experiment design strategies to understand how far away is a given machine learning model from that goal. You can also think of it in terms of Turing test, which is, let's say, if you've got human assigned labels to objects that, for example, this is a mouse or this in front of me is a laptop. Let's say if you're doing object recognition, then let's say if we go ahead and design a machine learning model that takes pictures of different types of objects and predicts their class, then we can say that if the performance of the machine matches the performance of the human on a sufficiently large test set or validation set, then we say that the machine learning model has generalized to these unseen cases. So if we are not able to distinguish between the output, the prediction output of a human and a machine, then we say the Turing test, right? So you can also relate these experiment design strategies to the Turing test. Okay, so I hope that explanation would give you some motivation for how the experiment design strategies and the use of scientific method is important in machine learning. Okay, so we've talked about the workflow of a machine learning problem. We identify the problem, we collect data, we pre-process the data, we model the data, we train a machine learning model, and we validate its performance or test its performance on a small data set, and then we go ahead and deploy it. But we may be doing multiple rounds of this process, uh, and those rounds can have different objectives. For example, one of the objectives can be I want to find the best parameters from my model. Okay, so let's say if I want to use support vector machines, what kernel should I pick, and what should be the value of CB, or what type of different kernel parameters should I use? To answer this question, as well as other questions, we need to design an experiment that evaluates the performance of a given guess, that is a given setting of the machine learning model with a certain set of hyperparameters on a validation set. And we would like to compare the results from for different parameter settings so that we can draw some conclusions about what settings work, what classifiers work, what features work, and what features don't work. Okay, so let's say if you are interested in answering this question, is my model better than this data? Let's say if you do go ahead and design your own classifier and you want to see how it compares to pre-existing classifiers or someone of your friend's classifier, you can use these experiment design strategies that we're going to talk about in this part of the lecture to do that. And then you can have broader questions. Is it the case that this particular classifier, let's say support vector machines, is always better than, or most of the time it's better than this other classifier, let's say a perceptron? Now we talked about the theory that since support vector machines maximize the margin, therefore they should be better they should generalize better to most of the data sets that we would encounter in machine learning. But is it really the case? How can we go ahead and design an experiment to do that? Does this model work? Does this model produce better sensitivity? Is the training time of this machine learning model better than the training time of another machine learning model, let's say? If, is this classifier overfitting or poor at generalization? So all of these are variants of the same thing. We want to measure the performance, either accuracy over an unseen test set, that is generalization, or we want to measure some other aspect, let's say time, computation time, testing time, or training time of a given classifier. So we want to analyze the performance of classifiers, and we want to compare them. These features, we can also do the same thing for features. Let's say, do these set of features that I've extracted, are they a good representative for solving this particular problem? Let's say if you're given a problem of detecting tanks, what features would you use? You'd come up with some features and then you would train a classifier. Or your friend may come up with different set of features and come up with a slightly different classifier. Now we want to see or want to do a head-to-head comparison of these two different classifiers and want to see whether there's certain advantage in terms of generalization, in terms of computing time for of using a particular set of features. You can also use these same strategies to, let's say, how many training epochs should I do? Remember, a training epoch is how many times a classifier sees the training set and updates its weights or performs a certain optimization procedure. So you can essentially go ahead and analyze that using this strategy as well. Okay, so those are all the sorts of things that you can use these experimental design strategies. You can think of all of these strategies that we are going to talk about, cross-validation and all the performance metrics that we have in terms of sort of like debugging tools that help you understand what is failing in this whole life cycle of a machine learning model. Let's say if you see that you have trained your machine learning model, but it does not perform well on a given test data set, then you want to understand why that is not, why is it failing? So most of the time when we're building machine learning models, most of the time is spent in such debugging. We would be really lucky if you train a particular classifier on a given data set and get a very good validation performance the first time you run it. Okay, you have all the forces in the universe on your side, but most of the time what we'd be doing is trying to debug or to identify what's failing and why is the machine learning model not giving correct output. So to do that, we need to understand these experiment design strategies. For example, it may fail, particular machine learning model may fail because it is not able to capture the structure of the data. Let's say if the data is discrete, but your machine learning model makes certain assumptions that the data should be, let's say, continuous, and then it's not able to capture that structure of the data, it will fail when you give it an unseen test set. Okay, so it may fail in validation. The same thing goes here. The data is not linearly separable. Let's say if you want to separate using a linear SVM or a classifier or data set that is not linearly separable, then you may get some uh, get a lower performance than say if you were going to use a linearly classifier that allows for linearly non-separable data. So that can be the case. Some classifiers may fail if the amount of data is too small, if the data set is imbalanced, that is, if it has more examples of one class in the training and only a small number of examples of the other class in this training data set, the training data can be noisy. But to test that, whether it is noisy or not, we need to come up with a set of strategies that allow us to measure that. The test set does not follow the same distribution as the training data set, so that is called out of distribution testing. So we can have examples. We can have a test set that does not follow the same distribution as the training set. For example, you have trained your machine learning model on ECGs of patients from a certain ethnic group, but in your testing you can also get examples of persons from another ethnic group. So that creates problems for your classifier. So we want to understand whether that is the case. And each classifier, every classifier in machine learning has a set of inbuilt assumptions. And it's really important that you understand those assumptions. We haven't talked about assumptions underlying support vector machines and assumptions underlying k-nearest neighbor classifiers in too much detail right now. But I think you can very well imagine that each of these classifiers has a set of assumptions. So, for example, when you're trying to maximize the margin, you have an inbuilt assumption that the examples are that the boundary is going to be smooth, and the maximum margin separation boundary is the optimal boundary. Similarly, when we are talking about nearest neighbor classifiers, the nearest neighbor of a given example is going to be is probably going to be the correct class. So that is an assumption that we are making. So there can be so many different assumptions that a particular classifier in its design it has those assumptions, and those assumptions may or may not hold for a given problem. So, but to understand whether those assumptions hold or not, first of all, we need to understand those assumptions, and then we want to be able to measure the effect of those assumptions for a given problem. So that's where these experiment design strategies come in. So we can also have problems where the optimization algorithm may fail. Let's say if you've got a support vector machine, then we've got a single optima. But if the optimization algorithm fails, we will not be able to reach that optima or the minimum point that reduces the error. And that means your classifier may fail on the test set, right? Is the representation not sufficient enough? So all of these REO, each one of them can fail on its own. The optimization fails, you will not be able to generalize very well. If you have a representation that is linear, but the data set that you are working with follows a linearly non is separated by a nonlinear boundary, then your representation doesn't allow any richness or sufficient richness, or doesn't have sufficient capacity, as is a technical term for this. Uh, it will fail, right? So, and if your loss function doesn't measure the error for a given problem, then you can still fail. Your machine learning model can still fail. So, trying to understand what's going wrong or debugging what's going wrong in a given machine learning model, we need these strategies, these experiment design strategies to be able to do that. Okay. So the goal is, of course, accuracy evaluation. How good will a given machine learning model be in practice? And here I'm using accuracy very broadly. We're going to talk about a specific notion of accuracy, but here we are using this notion to mean generalization. So how good or bad a given classifier is on a given test set. So we want to be able to measure that. We want to measure the generalization accuracy. And we also want to do sensitivity analysis of a classifier. And is the classifier, for example, we may be interested in understanding whether a given classifier or a machine learning model is sensitive to the initial choice of weights that you started off with, or is it sensitive to the type of hyperparameters? So, for example, you can have a machine learning model that works when you specify C is equal to 100 and you use an RBF kernel with, let's say, a spread parameter of zero point 0.1. But as soon as you make a slight change to either one of these parameters, all hell breaks loose. Sorry for the explicit use of this term, but if a classifier is too unstable and it only works or it produces good results with a very specific set of hyperparameters and nothing else, then probably it's going to fail because it's not stable enough, it's not robust enough. So that's we don't want such classifiers. Some classifiers can generate very good generalization performance for a very specific set of test examples, but not for other ones. So those classifiers can be sensitive to choice of the data. We don't want such classifiers. We want classifiers that degrade, whose accuracy performance degrades in a relatively smooth way or gracefully, as so there's graceful degradation of classification performance, or there's only a small variation within due to the change in the data set. Some classifiers can be affected by randomness. You run them once, they work well. You run them the next time because they have some inherent randomness, especially neural networks that we're going to talk about in the rest of this module. Those can give you very different results when you run them different times. And we don't want classifiers to be too sensitive to randomness. So there is some variation in validation performance that it can be expected, but if it's too large, then we probably need to resolve that issue. Similarly, some classifiers sensitive to round of errors, or your machine learning model can be sensitive to round of errors. Measuring the effect of each one of these and other controllable or non-controllable factors is called sensitivity analysis, and that forms the core of performance analysis of a machine learning model. Typically, what people do is they train a classifier, they test it on a given test set, and everything is green lighted if the performance is good enough. They don't do any of these analysis, these sensitivity analysis. They don't do how robust a particular classifier is, but it's really important if that system is going to be deployed in practice. Okay, so those are the real objectives. We'll also be talking about some evaluation metrics, and by the word metric, I mean something that we can use to measure the performance of a given machine learning model. So let's say we've got a training data set for training a classifier, and we've got a test set, a small test set. Some people also call it a validation set. So these terms can be used sometimes interchangeably. But we'll define what's the difference between training, validation, and testing as we go through the module. Okay, so these three things are going to be uh, defined very clearly. But for now, the training data set is a part of the data set for which we know both the features and we know the labels, and we use this information to train the or identify the parameters, let's say the weights and the bias of a given classifier. Okay. Once we have trained the classifier on this training data set, we can go ahead and analyze its performance on a validation data set for which we know both the training and the test labels. Let's say you choose a particular value of a kernel. Let's say you use the RBF kernel and you want to understand what is the impact of that choice. You can train a classifier with a particular RBF kernel or a support vector machine with an RBF kernel, and you can test its prediction or its generalization on this validation set. Okay, and you can then use the same validation set for another setting or another kernel. Let's say you want to use the polynomial kernel with a certain degree. You can analyze the performance of that classifier on the same validation set. And based on that, you can go ahead and pick which of the two classifiers works better. So typically validation, so one of the differences for now that you can remember, training is used to select the parameters of a classifier, so the weights and the bias. Validation is used to analyze the hyperparameters of a classifier. For example, what kernel should I use? Okay. And then we report the generalization performance of a classifier on a test set for which we know both the training and the test labels. Training for which we know the features and the labels. However, we had already done the hyperparameters. That means we've already picked what the best value of those hyperparameters is using the validation set, and then we go ahead and report our performance on a given test set. So I hope this uh, would help you. We'll go over this definition, these definitions once again as we go through, actually many times through this module as we go along. However, for now, it's important that you understand that if the parameters of a machine learning model, such as weights and bias, are chosen using a training data set, the hyperparameters are typically obtained over the validation data set, and then we report the performance of a machine learning model over a given test set before it is deployed, and then the real test begins. That is, how does it perform out in the real world? Now, if a classifier fails in the validation stage, probably we can go ahead and change the hyperparameter setting, right? And we can pick a different value of the parameters. We can even pick a different classifier, and it can give us we can verify whether it works or not on the test set that we have. However, a classifier may pass the testing stage that we have over here, but it may fail out in the real world again. Okay, and then it's back to square one. Okay, so we can go ahead and redesign the machine learning model. So that's the strategy. So always remember parameters, for example, weights and biases. If you're using a data set to do that, we'll call that the training data set. If you're using a data set to train the hyperparameters or analyze the effect of the choice of a certain set of hyperparameters for a given problem, you call that data set the validation data set. And when the performance is going to be reported to, let's say, your customers, you typically have a test set that you keep as separate from both the training and validation. and you report your test performance on that. That's going to give you an estimate of how good or bad your classifier can be or is expected to be in the real world. So we have that test. So try to pause the you can pause the video and try to wrap your mind around this concept. Okay, the golden rule is the following: under no circumstances are testing labels to be used or testing or validation labels to be used in training or the training data in the evaluation of the generalization performance. It's a very simple rule, but it can be really hard to follow at times. So say it with me. I would say that under no circumstances are test or validation labels to be used in training. We'll not be doing hyperparameter tuning, or we will not be doing parameter tuning using label information from the test set or the validation set. We can do hyperparameter tuning using the validation dataset, but the test dataset, its labels are not to be used in training or in hyperparameter setting, right? Then we have the training data that is not never going to be used. It should never be used in the evaluation of generalization performance, and that makes sense. It's kind of like cheating. You already know the answer to that because you've already given the classifier the answer to that question, and then you give it the same thing in testing, so it's going to do really well. But once it that doesn't guarantee generalization because it doesn't give me confidence that the same classifier is going to perform very well out in the real world, right? So that is why we follow this simple rule. So um, your throughout this module, as well as your overall goal of working in data mining, this always keep this in mind. Okay, and it kind of makes sense. If you already know the labels of something, why are you designing a machine learning model to predict that, right? So whatever you do, always think of how that machine learning model is going to be deployed. So if there is a piece of information that you cannot have for uh, for a classifier during its practical testing, don't use that information for performance assessment of that classifier. So let's say if you have a particular feature that cannot be computed at test time, you cannot use that in performance analysis. You cannot design classifiers. If you have a label, if you have got labels that are only available for your training, those will not be available for testing, so you cannot use that information for performance analysis. Anything that cannot be available for testing for in the real world, or when the classifier is deployed, or when the machine learning model is deployed, should not be used for performance analysis. That's the golden rule here. All evaluation metrics, and the other thing to remember is, although there are a bunch of evaluation metrics, but all those evaluation metrics have underlying assumptions. And we should understand or make an effort to understand those assumptions, because you can pick uh, pick up evaluation metric that shows that your classifier is doing very well, but on with respect to that metric only. But out in the real world, it may fail. So all of those, because it doesn't satisfy those assumptions. So all evaluation metrics have underlying assumptions, as we are going to see, and they have limitations of where you can and cannot or shouldn't apply those. And we should always remember those. So those limitations and assumptions. So what we are going to do next in the rest of this lecture on evaluating and comparing models is we're going to talk about different metrics. For example, accuracy, we will be talking about AUC, ROC. What that is, I'll just explain, but we'll be talking about those. But the more important or the bigger goal here is to understand those assumptions and limitations that lie at the core of those metrics, so that we know where we should apply those and where we shouldn't be applying those. Okay, so that's the real goal here. So with that, I'm going to go ahead and start talking about different types of metrics now. But so far what we have done is we've talked about overall philosophy of why we should be designing, why should we be doing experiment design for comparing and evaluating performance analysis models. It's to pick the best model that for out of a choice of different machine learning models. Let's say if you've got 10 different models, you want to pick which classifier to use, whether you want to use a k-nearest neighbor classifier, whether you want to use a support vector machine, or whether you want to use a deep neural network, What are those hyperparameter choices that you are going to pick? What is, for example, what kernel are you going to pick? What is the value of k and k nearest neighbor you're going to pick? If your classifier starts failing, then these experiment design strategies are going to help you identify or debug uh, that particular problem. And to be able to do that, we need to be able to measure how a given classifier is performing on an unseen test set. And to do that, we have identified what is meant by training, what is meant by validation, and what is meant by testing. So I hope that is clear to you. And then we are going to define different metrics so that we can measure that. And there's a very good maxim that says if you cannot measure it, cannot measure how good or bad something is, you cannot manage it, you cannot fix it, right? And what we want to do is we want to measure how good or bad a given classifier is on a given test set. Okay. And for that, we are going to study different metrics. We are going to talk about the assumptions and limitations of those metrics.